J. Thomson became the third Cavendish Professor of Experimental Physics in 1884. One of the phenomena he studied was the conduction of electricity through gases. One subject which interested Thomson was cathode rays. These rays are emitted at cathodes, or negative terminals, in discharge tubes, like this one, or this one. In 1879, Crookes had proposed that the cathode rays were radiant matter, negatively charged particles that were repelled from negatively charged cathodes and attracted to the positively charged anodes. The nature of the cathode rays was controversial. Although Thomson thought that the rays must be particles, many Europeans thought they were an ethereal disturbance, like light. In Germany, Hertz had observed the rays passing through thin sheets of gold. It seemed impossible that particles could pass through solid matter. J. Thomson realized that he could deflect the cathode rays in an electric field produced by a pair of metal plates. One of the plates was negatively charged and repelled the cathode rays, while the other was positively charged and attracted them. He did this experiment and was sure to allow for a vacuum in his tube so as to ensure the gas inside was not ionized. When he passed the beam through a uniform electric field, a deflection occurred. The cathode rays had moved towards the positively charged plate, therefore we can determine that the overall charge of the beam was negative. J. Thomson had used an electric field to deflect the cathode rays, proving that they were in fact negatively charged. A current in a coil of wire produces a magnetic field. Two coils, arranged as a Helmholtz pair, will produce a uniform magnetic field. A beam of charged particles passing through the magnetic field will be bent at right angles to the field into a circular arc, or even a complete circle. The magnetic field produces a force which deflects the cathode rays. In his tube, Thomson positioned the coils so that the deflection was in the opposite direction to the deflection produced by the electric field. By adjusting the strength of the field, the rays could be deflected in one direction by the electric field and back in equal amount by the magnetic field. The forces were balanced. Since the forces were balanced, he could use the two equations F equals EQ and F equals BQV, and rearrange them to make EQ equals BQV. Therefore, the charge cancels down, and we are left with E equals BV. To find the velocity, we rearrange E over B equals V. Since both E and B are findable, V can be calculated. By turning off the magnetic field, Thomson could measure the deflection of the cathode rays in the electric field alone. This deflection is due to the cathode rays acquiring velocity in a direction parallel to the electric field. The velocity of the particles, perpendicular to the field, remains constant. This new velocity parallel to the field equals the acceleration in the field divided by the time in the field. The equations used to relate this to the deflection angle are shown in this diagram. The field strength, E, the distance over which it acted, d, and the angle, theta, are measurable, and Thomson had already calculated the ray's velocity, v. Therefore, by measuring the deflection, Thomson could calculate the specific charge, q over m. Once the charge on the particles was measured, he could say with absolute certainty that they were 2,000 times lighter than hydrogen. This explained how they could pass through thin sheets of gold. Particles this small could pass between atoms in a solid. He concluded that the particles, which he called corpuscles, were a universal constituent of matter. They form part of all the atoms in the universe. We now know these particles as electrons.